I'm Adi Iyengar. Um, a little bit about me. My pronouns are he, him. I've been working as a senior software engineer in Elixir for 5+ years. My GitHub username is the bug catcher. Twitter is laybugcatcher. The bug catcher was unavailable. And love catching software bugs. I love test-driven development, Elixir, and theoretical physics. And you can hear me talk more in the Elixir Mix podcast these days. If you're not aware of it, you should check it out. I'm also currently authoring an Elixir book. So it's called Build Your Own Web Framework in Elixir. I'm a huge fan of Learn X by building it. So this book is kind of, it follows that methodology. Hopefully it'll be published in April 2022, and working with Pact Publishing for this book. It also has a full dedicated chapter on metaprogramming, which is like the biggest chapter in the book. So if you like this talk, you should check the book out. Or also just if for whatever reason, if the book is like out of your price range, just hit me up. We'll find a way to get it to you. Awesome. So let's look at the talk today. We'll be covering the fundamentals of metaprogramming. We will look at pros and cons of metaprogramming and when to and when not to use it. It's a touchy subject, metaprogramming, so it's like important to kind of set the foundation by covering these things. Then we'll get into metaprogramming in Elixir, how Elixir does it and how it is different from some of the other languages. We'll look at some metaprogramming examples and how we can analyze, like libraries like Ecto or Phoenix and what things they do good, what things they potentially don't do good. And we'll talk about testing metaprogramming, and we'll briefly touch on reflections, and hopefully at the end we'll have time for Q&A. Also, I recently gave this talk, I think a few months ago at CodeBeam Europe. I made this different enough that if you were there at that talk, you could still get something out of this. For starters, it doesn't have live coding, so it's a lot less pressure on me and a lot more preparation to prepare slides. But yeah. All right, so what is metaprogramming? The simplest way to describe it is that it's code that writes code. You must have seen this line, at least 10 times in your life. And a metaprogram, a program is considered metaprogram if it generates code, analyzes other code, stores information about other code, injects behavior into another code. And this is like, where Elixir kind of shines. And really any code that treats other code as arguments or data, therefore it's a code of a higher order, is considered metaprogram. And the language that's used to write the metaprogram is called the meta language. There are languages like Elixir, whose meta language is themselves, and that feature is called reflectivity. And what that allows you to do is it allows you to extend, Elixir's functionality in Elixir itself. I've heard this story that 90% of Elixir is written in Elixir. I have not fact checked it, but I've heard it. But such things are possible because of reflectivity. Great. So let's get an example. Let's get the Phoenix router. Something most people must have seen a few times. So let's say we're defining a pipeline API that accepts JSON requests, add a scope for API, and any request inside that scope go through the API pipeline defined earlier. And boom, we can just define a route that goes to API controller's index action. So all of this, was possible in like 9 lines of code. So looking at that, let's look at the pros of metaprogramming, right? It hides complexity of implementation. So you just have to focus on, as a user of the DSL, you have to focus on what is happening instead of how or why it's doing what it's doing. Therefore, it increases developer productivity. You don't have to write like a lot of extra code. You can just focus on, more like, descriptive programming, right? And it automates and, more importantly, standardizes the otherwise tedious boilerplate code. I think automates is great, but metaprogram is a great way to standardize code that can be done in multiple ways. So you kind of your maintenance of the code that uses your interface is a lot less and easier to manage. So there are a lot of cons of metaprogramming. Some of them are it decreases transparency, and this is on the flip side of heights complexity. Increase overall code complexity. Even though the complexity of the interface is a lot less, the implementation becomes a lot more complex and harder to maintain. It's hard to maintain, extend, test, debug. It's a lot more opaque generally. So there are ways to get around that, but generally these are the cons of metaprogramming. So people ask me, what should you do before considering metaprogramming? And the simplest answer, obvious answer, is try to implement a solution without any metaprogramming. There's two advantages of that. You'll either most likely write your entire solution without metaprogramming, or most of your solution will be, non-metaprogram. So what that will do is it allow you to write an implementation which is simpler because it doesn't have metaprogramming, and just wrap it in a metaprogramming shell. And it makes it more maintainable. Your metaprogram could be more separate from your implementation and can be maintained separately. Try to implement a solution without any metaprogramming first. All right, when to use metaprogramming? First one's, again, pretty obvious when you've exhausted all the other options, right from Chris McCord's book. When you know that it'll be used at multiple places, I've seen a lot of people kind of, being proactive towards defining their interface. And what that does is, if once you use it at another place, you have to trash the entire thing and rewrite the interface because your requirements changed. So it's good to wait until you wrap your implementation in an interface. Also, similarly, when the requirements are less volatile, it's a great place to use metaprogramming in. When you've minimized the metaprogram code, like we talked earlier, try to write your implementation without metaprogramming. And since metaprogram is more complex, it's less deterministic. So when you've added ton of unit integration tests, it's safe to use metaprogramming then. When you've maximized its inspectability, so I think the best DSLs, the best metaprogrammed libraries are the ones that have a lot of introspective features. What that does is it allows people to extend it. It allows people to test it, debug it better. So when you've put thought into that, it's good to use metaprogramming. And when you've restricted its usage, by either proper compile time errors, you want to think about all the ways developers can break it, and try to get those errors to compile time and descriptive errors instead of it breaking in runtime. And when the cost of failure is minimum, and this is something because it's complex, it's good to think about. So I'm a lot more comfortable using metaprogramming for making tests more efficient than injecting something in production, for example. All right, now that that's out of the way, let's talk about metaprogramming in Elixir. So metaprogramming in Elixir is a way to extend its functionality. There are three constructs, three pillars of metaprogramming in Elixir. The first one is quoted literals. Second is behavior injection through macros mostly. And third one is compile time callbacks. So let's talk about quoted literals or quotes. So quoted literals in Elixir are Elixir representation of the abstract syntax tree, AST. So AST, for those who don't know or don't remember, is the tree representation of all the tokens of your code that happens after syntactical and lexical analysis of your code. So here's the Elixir quoted literal Elixir representation of AST for A times B. So it's, as you can see, a 3-element tuple. Feels weird to say something is a 3-element tuple, but anyway, a quoted literal is a 3-element tuple. The first element is the function. Here it's atom times. Second element is metadata, usually contains the modules that are imported, or the context in which you're running the code, or the context in which the quote was created. And the third one is the list of arguments for the function. So you can use the first one and the third one to create like a tree. So how can you convert code to quoted literals, or AST? So you can use a quote keyword. What it does is it converts any Elixir code to quoted version of that. So if you do quote 1 + 2, boom, it returns a 3-element tuple with plus, metadata, and 1 and 2. And also, by the way, I'm going to have a few IEX examples here, just so you're aware. Right, so let's represent another quote as an AST. And this one's a little bit more complex. There's 3 operations here. So it's quote do 1 + 2 × 4 - 3. I've hidden the metadata. So it's got 3 operations. And if we try to represent that as a tree, it's going to look something like this. Where times is the root, plus and minus are the operands, and 1, 2, 4, and 3 are the leaves of the tree. Great. Now let's talk about evaluating quoted literals. There's a function called code.eval_quoted that allows us to evaluate a quoted literal. It takes 3 arguments. The first one is a quoted literal you're evaluating. The second one is the context in which you're evaluating the quoted literal. And third is a list of variable bindings that you send to the quote. And it returns the result and the variable bindings in which the literal was evaluated. So here's an example. In IEX, let's define a quoted literal 1 + 2. We get a 3-element tuple. Then we evaluate it, and 1 + 2 is 3. So we get the result 3. And since we didn't define any variables within the quoted literal, we get an empty list of variable bindings. Great. So let's now see what happens if we just do quote 1 + a, and a is not defined. So we get a 3-element tuple again, but as you can see over here, it's 1, and a is not just a as an atom. It's a little bit, it has some more metadata attached to it. We're not going to get into that in this talk, but it's a really cool way Elixir prevents some ways we can break things. So it's got like information of scope and all that stuff. So great. So let's evaluate the quoted literal. We get undefined function a, as expected. Okay, so let's define a equals to, define the quoted literal. Again, we get the same quoted literal. Try to evaluate it, we get there again. What that means is if you define a variable outside of the scope of the quote, it doesn't leak into the scope of the quote, or at least by default, it doesn't. Similarly, let's define something inside the scope. So let's say quote a equals 10. Again, we get this beautiful syntax tree. If we evaluate that, it says it's successfully evaluated. But if we try to call a, we get undefined function a. So what does this mean? Variables defined inside the scope don't leak outside, and variables defined outside don't leak inside. And that's referred to as hygiene in Elixir. Great. So how would you evaluate that quoted literal 1 + a, We can manually merge them because we know they're 3-element tuples, So we can define a quoted literal 1 + a again. Let's define another quoted literal where a equals 2. Now what we want is we want a equals 2 to happen before 1 + a. So we can define a new quoted literal, block manually. Block is the function, doesn't need any metadata. And we add the other quoted literal a equals 2 first, and then 1 + a as its arguments. And then we evaluate that block, and then we get 3. And we also get a equals 2 because it's defined within the quotes context. So just to emphasize that quotes are literally 3-element tuples. You can define that and evaluate that, right? Awesome. Let's talk about var. There are better ways of injecting, kind of variables across scope, and var is a way to, kind of break that hygiene and do it at the time of evaluation of the quote or literal. Yep. So it's a way to pass a variable to the quote at its evaluation time. So we define a quote instead of 1 plus a, it's 1 plus var a. Again, it's going to look a little bit different over here. But if you evaluate that, but you also send a variable binding a is 2, it gets evaluated to 3 and returns that a is 2. So this is like unhygienic because you're leaking variable across scopes. So you should be careful about using this. There are instances where I've used it, but you can easily avoid using it in most cases. Another way you can inject more dynamic behavior to your quoted literal is unquote. But this is a way to pass a variable to the quote at the time of its definition, unlike var, which was time of evaluation. So let's take a look at this. So we define a equals 2. When you define the quoted literal, we just do unquote a. And as you can see right here, when it's evaluated, it knows that it's 2 before you even call quote.eval quoted. So that's where unquote is different from var, where it's not unhygienic because you're not injecting variable across scopes at the time of evaluation. So when you evaluate it, we still get 3, but again, no variable bindings because it was at the time of definition of the quote. Great. So now we have all the ingredients we need to do code injection. We don't need macros right now, right? But this is code injection the bad way. We can use quote eval quoted, and let's define a module behavior and define a function quoted behavior, right? And that function just returns a quoted literal that defines a function hello, which returns world, right? Great. Now let's define another module behavior tester, manually call code.eval quoted with the quoted behavior function. So whatever that returns, a quoted literal, and evaluate that in the environment of the module. What that does is if we compile it and call behavior tester.hello, we get world. So we've injected behavior from one module to another by calling code.eval quoted. Now this is bad because you have to manually pass variable bindings. You can change environments in which it's evaluated. And if you're compiling multiple modules at once, it could get very tricky. So there are better ways of doing code injection. Elixir has macros, which allow us to do that. The documentation says macros are compile time constructs that are invoked with Elixir's AST as input and the superset of the AST as output. What that essentially means is macros take ASTs and return ASTs. And they are defined using def macro, which itself is a macro, right? It's really cool. It's really cool. So let's look at an example of a macro. So let's define a module, macro module. And inside the macro call, let's add an inspect, right? Underscore module and Elixir returns the current module in which the code is called. So let's label it as it's outside the quote, right? And inside the quote, let's inspect module and see how these are different. So when we define the module, we have to require the module that houses the macro and then invoke the macro. Great. Let's compile it and see what happens. So when we compile it, we see, okay, outside the quote, the module is macro module, but inside the quote, the module is caller module. So anything you put here inside the quote literal gets evaluated in the caller module, but anything you put here gets evaluated in the macro module's context. That's something important to understand while using macros. All right, now let's try to do code injection again using macros. So instead of defining a function quoted behavior, let's add def macro quoted behavior. Everything else stays the same. And because this is inside the quote, this will be evaluated within the caller's context. And instead of doing quoted, eval quoted, and all this dirty stuff, we can just do require behavior and invoke the macro right here. So if we compile it, again, behavior hello returns world. So this yields the same result, but it's a lot cleaner, and Elixir wants us to do code injection this way. Let me just check how we're doing on time. Okay. All right, so code injection the better way. Elixir prefers we use __ using macro over just any macro, because it can be invoked using use keyword. So if you replace quoted behavior with using macro, you can just call use behavior instead of requiring and calling the macro explicitly. Again, you get the same result. All right, the last pillar of metaprogramming in Elixir is compile time callbacks. So these allow us to hook into the compilation of a module, and they can be used for logging, tracing, and also injecting behavior. There's 3 types of compile time hooks: before compile, after compile, and on definition. So before compile is registered using the before compile module attribute. It's invoked right before the module is done compiling, as the name suggests. And it just takes a module's environment as argument, and it can either be a function or a macro. But since the module isn't done compiling, it needs to be in a separate module. So let's do behavior injection using before compile, right? So we replace using with before compile, and just register the callback with at before compile, and we get the same result. But we get the same result only in this case. There's a difference between calling a macro and a before compile, because a macro gets expanded right there, but a before compile gets registered here, but it gets invoked at the very end. So there's other body in the method. Even though you put before compile here, it will be called at the end of the compilation of the module. Great. After compile is registered using after compile module attribute, invoked right after the module is done compiling, and it takes 2 arguments, environment and bytecode. It can either be function or macro, and it can be the same module itself. Here's a quick example. We define an after compile callback that's in the same module. All it does is prints that done compiling module, right? So once we compile the module, it prints done compiling module. So again, it's invoked right after the module is compiled. I'm going to have to pick up the pace a little bit over here. Okay, so the last one is on definition. It's registered using on definition attribute. It can it's invoked whenever a function or a macro is defined, and it takes 6 arguments. We're not going to get into what those 6 are, but this can only be a function, and that's so you can, Elixir wants to restrict you what you can do, and restrict ways in which people can break it. And it also needs to be in a separate module because the module isn't done compiling. Great. So here's an example. There's an on-def module, and we define an on-definition hook. And it takes 6 arguments, as you can see, but we just use name and the body of the function. And all it does is prints defining a function or a macro with the name, and body, a string version of the body. Great. And once you register it like this and say I define a function hello, on compiling, it prints defining a function or a macro with the name hello and body hello puts world, right? So exactly the body. So those are compile time callbacks. Now that we know all the pillars of metaprogramming Elixir, let's look at some examples. First one is vector schema. So again, it's a pretty good DSL where you can define a schema of a module. You can just use a schema and define all the fields. Post has a title, body, and an array of comments. Let's see how it would be implemented. Just to some extent, we're not going to write vector schema right now, but just like some important parts. Of course, it needs to have a using macro because we use vector schema. And what that does is it imports Ecto schema, and it might do some other things, but this allows us to put all the macros in Ecto schema module, not inside the quote. So they'll be easier to test. And embedded schema takes a block, and inside that you can pass fields and all that stuff, right? And on top of defining an interface with primary key and all that stuff, it does def struct, right? Ecto allows us to also define a struct based on the fields. So that's what embedded schema would kind of look like, right? So that's kind of what Ecto schema looks like. But on top of that, Ecto schema also adds reflection, and that's where it shines. I think Ecto generally shines because of reflections and how introspective the code is. So let's take a look at that embedded schema again. They define a function chainset, which returns it's underscore chainset, which returns all the fields that can be used in chainset generally or expected. Like doesn't have ID or like timestamps, but everything else, right? The best part about that is our schema reflection API. You can get all the fields, all the type and type of each field, associations. It's really awesome, and this has really helped me in a lot of ways, especially while writing more deterministic tests. So here is an example of test, right? Let's look at the post module again. We know it's an embedded schema, right? But there's no way to test it that it's an embedded schema. We can test it using reflections. In the post test, we can describe schema and say it's an embedded schema without a primary key. And we can say that the source of the schema is nil. That means it doesn't have a table or a source corresponding to it. And that's because of the schema reflections DSL or API. And we also know its primary key is nothing because it's an embedded schema. Great. So Ecto has a lot of introspective features, not just schema. There's chainset, for example, has like all the validations. The struct has all the validations, required fields. So you can really test your chainset function without really actually trying to insert the data in the database, which is what most people do. So you should check out Ecto and how all the reflections are designed in Ecto. Another example is Phoenix Controller. It's not nearly as introspective as Ecto. It's still great, but here's an example. So let's say we have a page controller, right, that just uses example web controller, pretty regular. Let's say we call a plug require claims. All that does is that it checks whether the token or the requester has the ability to, hit a particular action. So let's say it can hit index if it has claims page read, right? This should look familiar to most people. And similarly for all the other actions, show, create, delete, have their own claims. And it has all the actions down below. So how do you test this usually, right? Conventionally, we write like a contest, right? Using example web con case. And we say, okay, we had to test for all the positive use cases and all the use cases for every plug, right? And say, okay, it responds with a 403. We put bad claims. We try to go to the page and we assert that, okay, we get a 403, right? And the connection is halted. Now you have to write this test for every actions, every use case in every controller. We all know that doesn't happen, right? It's like a lot of tests to write it to copy paste a lot of tests. And it slows down a test suite because all of these are complete request tests, right? You don't have to write that once you've tested the plug. So we can test using reflections, right? Now, since Phoenix Controller doesn't have reflections, it's a little tricky. Now, here's what I want to get. I want to be able to do, okay, describe required claims and just say, okay, sets up required claims with correct options, right? So I'm testing the usage of the plug instead of the results of what happens when you use the plug. So I do assert uses plug, the controller, what plug you use, and what options you're sending, right? And basically that itself should test all the use cases, assuming the plug itself is tested sufficiently. But like we said, there's no plug reflections in Phoenix Controller. So we can use Metaprogramming to build reflections. So once you look at the Phoenix controller pipelines code, the macro plug that's invoked, it's delegated to a private function plug. And that function takes a few options, does a lot of things, but towards the end, it caught my eye what it does. It adds a module attribute, which kind of stores what plugs you've called, what options and guards and all that stuff, right? But it's not persisted. So we have to find a way to get this information. So once we get add plugs, we can use that to list all the plugs for a controller, right? So let's go to example web where the controller function is defined. And inside the code, let's define __ plugs that just returns add plugs, right? That should do it. Now we have access to plugs by calling this, non-private function. Unfortunately, it won't work because this needs to be called at the very end of the controller, right? Because you can call plugs after you call use controller, right? We know there's a way to do that. We can do that by using before compile. So instead of defining the function right there, you register a before compile callback and delegate it to a different module. And what that does is it defines the before compile callback and defines the function __ plugs, which just returns the state of module attribute at the very end of the compilation. And since it's at the very end, it will have all the plug calls. So now we can use __ plugs to develop that reflections API that we want to test controllers, right? Assert uses plug. I'm not going to get into how. It's, again, pretty straightforward. You can just call controller.plugs and get plugs and see if it has a plug with those attributes. So again, a quick tip here is to add reflections API to your DSL so others can test it. So what I usually do is whenever I have use or using macro, inside the quote, you do your thing, and then I add usage options. All that function does is returns what options you called while calling use. So it allows you to test your use calls without testing, the module's use cases again. Or you can be like, okay, A is tested, and I know that B uses A. I just want to test if A was called with correct options. That's it. And if you're using a different interface that doesn't have that, this is something I don't recommend. This is something I came up with. You can add reflections on your own, like we did for plugs, or you can do something like this. I define a module called introspective kernel, and that has an introspective use function. So instead of use B with options, I do introspective use, which I define in a different module. And all that does is introspective use takes a module and an options, quotes, registers an attribute, introspective uses, which accumulates and persists after the module is compiled. So you have access to that after the module's compilation. You can call use right there, and at the end, store what you're using. So once the module is done compiling, you'll have a list of what you've used if you use this. Again, I don't recommend using something like this unless you really want to. This is something I use in my side projects because I'm really obsessive about testing everything. But yeah, so summary. In Elixir, there's 3 pillars of metaprogramming: quarter literals, macros, compile time callbacks. Metaprogramming should be used very carefully as the code becomes more complex. You need to put more thought into it, try to make it more reflective, try to minimize the code, metaprogram code. And a DSL that's a result of metaprogramming should be idiomatic, introspective, testable, and clearly separate from implementation, which will make it a lot more maintainable and digestible for people who are using it. So that's pretty much it for today. I'm ready for any of your questions.